This is the video for Module 14, Section 4.1, about solving systems of linear equations by graphing. First, we're going to just talk about graphing linear equations. And a linear equation in two variables is an equation that can be written in the form ax plus by equals c, where the a and the b are not both 0. This form is called standard form. Here's some examples of linear equations. Not all of these are written in standard form. This first one here is because we have both the x and the y terms on the left side and only a constant on the right side. The second one here is not written in standard form because the y term is on one side and the x term is on the other side. This one would be written in what we call slope-intercept form. And this third one is also not written in standard form, but it is a linear equation because it has an x term and a y term and a constant. There are no x squared or y squared terms or any higher powers of x or y. When we look at linear equations like this, the graph of a linear equation is a straight line. So a linear equation has solutions that correspond to ordered pairs, and every ordered pair solution corresponds to a point on the graph of the line. In this section, we're just going to talk about graphing linear equations by plotting points. So when we have a linear equation, in order to plot points, we're going to start out by choosing any value for either x or y. Then we'll take that value and substitute it in either for the x or the y, and then we'll solve the equation for the remaining variable. So if we have a linear equation and a table like this with the x and the y, we're just going to fill in the table with the x and the y values. We'll be repeating this process to get at least two ordered pairs because it takes 2 points in order to graph a line. So we'll plot the points using the ordered pairs in the table, and then we'll just draw the line through the points. And the table that's shown here has room for 3 ordered pairs, or 3 points. But keep in mind that you really only need 2 in order to graph a line. Here's an example. We're going to find 3 ordered pair solutions for the equation 2x plus y equals 10 by completing the table that already has some values filled in. Then we'll use those ordered pairs to graph the solution of the linear equation. We're starting out with x is equal to 3, so we're going to take our equation, 2x plus y is equal to 10, and in place of the x, we're going to substitute 3. That gives us 6 plus y is equal to 10. Now we're just solving for y. So if we subtract 6 from both sides, we end up with y is equal to 4. So that's going to give us one ordered pair, or a point, that we can plot. Now for the next row in the table, we have a value for y of 2. So let's plug that one in. So this time, we're substituting for the y instead of for the x. We're putting the 2 in there for y. So now if we subtract 2 from both sides, that gives us 2x is equal to 8. And then if we divide both sides by 2, that's going to give us x is equal to 4. So now where our y was equal to 2, we've got x is equal to 4. And that's going to give us another point to plot, the point 4, 2. Now we could go ahead and plot these 2 points and graph the line. And in fact, when you're doing your homework in MyMathLab, it will actually only let you plot 2 points in order to graph a line. This third point we can use as a check, and we can go ahead and plot that and make sure that our other 2 points were correct for the line. So now we're going to use x is equal to -1. So we're substituting in -1 for the x. That gives us -2 plus y is equal to 10. If we add 2 to both sides, we're going to end up with y is equal to 12. So this would give us the point -1, 12. Now let's plot our points, and remember that the x is left or right and the y's are up and down. So for the point 3, 4, we're going to go to the right 3 on our graph and then up 4. And there's our point. And let's go ahead and label that so that we know what we have. Then our next point we're going to plot is the point 4, 2. So again, we're always starting at the origin. 4 means that we're going to the right 4. And then 2 means that we're going up 2. So that gives us our point right there. Now, as I said, we could go ahead and graph the line with these 2 points. And in fact, our third ordered pair, we won't even be able to see on this graph because we don't have quite enough room going upwards. If we were going to plot that point, negative 1, 12, we would go to the left 1, and then we would go up 12. So it would end up being up here. So there's our point roughly up there. We can still use that to make sure that our line looks right. So let's go ahead and draw that in there. Now let's use our first 2 points, and we're just going to draw the line through them. And we can continue the line up here and see that our other point pretty much corresponds to the line. Since I didn't have a graph up here, I didn't quite get up to the 12. So it would actually, our point would actually be a little bit further up. Okay, let's look at another example. For this one, we have the same idea. We have a table that's already started. So we're going to find the 3 ordered pair solutions. And then we're going to plot those ordered pairs as points and then graph the line from there. So let's start out with x is equal to negative 3. So we have y is equal to negative 1/3 times negative 3 minus 2. And if we take negative 1/3 times negative 3, we can cancel the 3's. And also, since we have 2 negatives, that's just going to be a positive. So that gives us a positive 1. So we end up with y is equal to negative 1. That's going to give us the point, negative 3, negative 1 to plot. Next, we have y is equal to negative 2. And pay special attention when you're working problems like this as to which variable you have to substitute for. Because in this one, we're substituting in for the y instead of for the x. So we have negative 2 on the left side is equal to negative 1/3 x minus 2. Now, in order to solve this, we could start out by clearing fractions. But in this case, let's just go ahead and add 2 to both sides. So over here on the left side, we have negative 2 plus 2 is equal to negative 1/3 x. That gives us 0 on the left side. And then in order to get our x by itself, since we have negative 1/3, we could multiply by the reciprocal of that, which would be negative 3 times 0. That would give us x over here on the right side, and since anything times 0 is 0, we end up with x is equal to 0 for our solution. And our last one is y is equal to 0. So again, we're substituting for the y. And again, we're going to add 2 to both sides. That's just going to give us a 2 on the left side And again, to solve for x here, we're going to multiply by the reciprocal of negative 1/3, which is negative 3. So on the left side, we have negative 3 times 2 is equal to x, so that gives us negative 6 for x. Okay, now let's plot our points. Our first one, we had negative 3, negative 1. Then we're going to have 0, negative 2, and finally negative 6, 0. For our first one, negative 3, negative 1, the negative 3 tells us to go to the left 3. So 1, 2, 3 to the left. And negative 1 tells us to go down 1. So there's our first point. Our second point is 0, negative 2. So since the x is 0, we're not going to the left or to the right. We're just staying right there on the y-axis. And then we're going down 2. So there's our second point. And finally, our third point, which is a point that we can use to check, is negative 6, 0. So since the x is negative 6, we'll go to the left 6. And then since the y is 0, we're not going up or down, we're just staying there on the x-axis. So there's our third point. So now we have 3 points, and even just looking at them, you can tell that they're all in a line. We've done a good job with finding our solutions. So here's our line going through those 3 points. And remember that not just the points that we've plotted, but every point on this line would give us a solution to our equation. If we looked at some other points on this line, then they would also be solutions to the equation that we had. Now that we've reviewed how to graph a linear equation, let's talk about systems of linear equations. A system just means that there are 2 or more linear equations. So when we're talking about the solution of a system of linear equations in 2 variables, it's any ordered pair that solves both of the linear equations. For example, if we have the system x plus y equals 9 and x minus y equals 1, then for the ordered pair negative 4, negative 5 to be a solution of the system, it has to be a solution for both of the equations. In other words, it has to be a point on both of these lines. So one way we could tell whether this ordered pair is a solution of the system is just to use the negative 4 for x and the negative 5 for y, and plug those into both of the equations and see if we come up with true statements in both cases. So let's look at our first equation. And we're plugging in negative 4 for x, negative 5 for y. And then if we take negative 4 plus negative 5, we get negative 9. And that's what we have on the right side, so that checks. Then if we look at our other equation, we have x minus y is equal to 1. Again, we're plugging in negative 4 for x and negative 5 for y. That gives us negative 4, and since we have 2 minuses in a row here, that's the same as plus 5 is equal to 1. And if we take negative 4 plus 5, we get 1. So that one checks too. And that means that our answer is yes, it is a solution. Now, if it had worked in one of the 2 equations but not the other one, it would not be a solution. Let's look at a couple of other examples. So all we're doing here is determining whether the ordered pair that we're given is a solution for the system, which just means we're going to plug the ordered pair into both equations in place of the x and the y, and see whether we get true statements or not. So let's start with our first equation. And our x is -5, our y is -3. That gives us -10 plus -3. And if we add those two, we would get -13. Well, -13 is not equal to -7, so this is false. And that means that our point is not a solution. Let's try our other example. If we plug in 2, -4 into both of these two equations, four times 2 is 8, plus -4. Well, 8 plus -4 is 4, so that one checks. Now we also have to check the other one. In this first example, notice that we could stop after that first one because it didn't work. So we automatically knew that we didn't have a solution for the system. So here we're plugging in 2 for x and -4 for y. That gives us 4 is equal to -12. And -4 times -4 is +16. So we have 4 is equal to 4. So that one checks. So this one, our answer would be yes, it is a solution. In this section, we're just going to be solving systems of linear equations like this by graphing. And since a solution of a system of equations is a solution that's common to both equations, that means it also has to be a point common to the graphs of both equations. In other words, it has to be a point on both lines. What we're going to do in this section is graph the equations and see where the lines intersect, because that will give us a point that's on both lines. Now, if the system has at least one intersection point, or at least one solution, it's called a consistent system. But if the lines don't intersect, which would mean that they are parallel, then the system has no solution. And this kind of system is called inconsistent. Now, if we get two different lines in our system when we graph, then we say that the equations are independent. But if both equations represent the same line, then we actually have an infinite number of solutions for our system, and we would say that the two equations are dependent. Here's an example. We're going to solve the system by graphing, and then we're going to decide whether the system is consistent or inconsistent, and whether the equations are dependent or independent. So all we're going to do is graph the two lines, and then look for an intersection point, or decide whether they're parallel or whether they represent the same line. So for each line, we're just going to make our own table for our x and y values. When you're graphing like this, you don't have the values already picked out for you, so you can just decide on any value for x or y, as long as you make it one that's going to fit into your graph. Some easy values to pick are 0. So in this one, let's pick 0 for x to start with. So if we have x is equal to 0, then we're plugging in 0 for x. That makes this whole part 0. And that gives us y is equal to -4. Now we need one more point, or one more ordered pair, in order to be able to graph the line. So let's try using 0 for y this time. So now we're plugging in 0 for y. That gives us 4x is equal to -4. If we divide both sides by 4, then that gives us x is equal to -1. Now let's go ahead and plot our points and graph this line. So our first point would be 0, -4. So we start at the origin and just go down 4. And then our second point is -1, 0. -1 means we go to the left one, and 0 means we stay there on the x-axis. So there's our second point. And we do want to go ahead and graph this line so that we don't get confused later with the points from the other line. And when you're solving systems by graphing, it's important to graph as accurately as you can, because you're going to be trying to pick out the solution by where the lines intersect. If you don't have an accurate graph, it's going to be very hard to tell where the lines intersect. So there's our first line. All right, now let's find two ordered pair solutions for our second line. And for this one, again, let's use x is equal to 0. So that gives us 0 plus 2y is equal to -2, which means 2y is equal to -2. If we divide both sides by 2, we get y is equal to -1. Now on this one, I'm not going to try to use y is equal to 0 because we'll actually end up with a fractional value for our x. And in your MyMathLab homework, it won't let you plot fractional values. So instead of doing that, let's use 2 for x. And when you're doing this with your homework, you might have to try several different values in order to get one that doesn't give you fractions. So if we use 2 for x, then we have 10 plus 2y is equal to -2. If we subtract 10 from both sides, then we get 2y is equal to -12, and if we divide both sides by 2, we have y is equal to -6. So now let's plot our points. We have the point 0, -1, so that's just down 1 from the origin here. And then we have the point 2, -6. So we're going to go to the right 2 and down 6, which puts us down here. So now we're going to graph our line through those 2 points. Okay, so here's our second line. And now we're looking for the solution of the system. So we're looking for where these 2 lines intersect. And this will actually be easier on your MyMathLab homework because you'll be able to tell more easily where the lines intersect. But it looks like our intersection point here is the point -2, 4. Now if we want to check that, we would take our ordered pair and plug it back into both of our equations and see whether we get a true or a false statement, like we did in the earlier examples. Now, since we came up with at least one solution, so we did come up with a solution for this, that means that our system is consistent. And since we had 2 distinct lines, then that means our equations are independent. Here's another example. So let's start out with our first equation, 4x minus 16y is equal to 12. Let's start out in this one with x is equal to -1. That gives us 4 times -1 minus 16y is equal to 12. So if we add 4 to both sides, then we have -16y is equal to 16. If we divide both sides by -16, that gives us y is equal to -1. Okay, now let's try y is equal to 0. That that gives us 4x minus 16 times 0 equals 12. So we just end up with 4x is equal to 12, and if we divide both sides by 4, we get x is equal to 3. So there are our 2 points we're going to plot. So for the first one, we have -1, -1, which means we're starting at the origin. We're going to the left 1 and down 1. And then we have the point 3, 0, which means we go to the right 0 from the origin, and then just stay there on the x-axis. Okay, so here's our first line. Now let's find 2 points for our second line. So for this one, let's start out by plugging in 0 for y. So that gives us 0 is equal to x minus 3, and then if we add 3 to both sides, we end up with 3 equals x. For our next value, let's try y is equal to 1. That gives us 4 is equal to x minus 3. Then if we add 3 to both sides, that gives us 7 is equal to x. Now let's plot our points. Our first one is 3, 0. So that means we go to the right 3 and stay there on the x-axis. Oh, and notice that gives us an intersection point already, because we already had that point on the graph of the other line. Now our other point here is 7, 1. So we go over 7 and up 1. Well, it looks like we have another intersection point here. So it looks like these are the same line. Now we could check that actually by seeing if 7, 1 is a solution for our first equation. So let's check point 7, 1 in our first equation. Substitute 7 for x and 1 for y. That gives us 28 minus 16 equals 12. And that does check. So that means that 7, 1 is a solution for both equations, and so is 3, 0. And that means that our two equations actually represent the same line. So for this one, we have actually an infinite number of solutions. Any point on the graph of the line would be a solution for both of these equations. Now, since we did find at least one solution, our system is still consistent. But since our two equations represented the same line, that means that our equations are dependent. Okay, one more example. Let's start out with our equation -x equals y. And let's just try 0 for x here. Well, that gives us y is equal to 0. So now let's try another value for x to get another ordered pair. Let's just try 1. And that's going to give us -1 for y. So our 2 points are 0, 0, which is the origin, and 1, -1, which means we go to the right 1 and down 1. Now let's graph our line between those two. Okay, there's our first line. And let's look at our second one, x equals 6 minus y. And in this equation, since it's already solved for the x, the easiest thing is just to pick out values to plug in for y. So let's try y is equal to 0. And that's going to give us x is equal to 6. And let's try y is equal to 2. That's going to give us x is equal to 4. So now if we plot our 2 points, our first one's 6, 0. We're going to the right 6 and then staying on the x-axis. For our second point, we have 4, 2. So we're starting at the origin and going over 4 and up 2. Now if we graph this line, now we have our 2 lines and we can't see any intersection point. In fact, it doesn't look like they're ever going to intersect. And in fact, these 2 lines are parallel. If you notice that, let's look at the origin and this point up here, we have 6 units between our 2 lines. And if we look down here, we also have exactly 6 units vertically between our 2 lines, which means that they're parallel. What that means for our solutions is that there's no intersection point, which means that there's no solution. And when we have a system with no solution, that means that it's inconsistent. But since we had 2 distinct lines, 2 different lines, our equations are still independent. Okay, here's another example. Now when we're going to look at our first equation, notice that there's an x but there's no y term. And that means that we can put in any number we want for y, and since there's no place to plug it in, then no matter what, we're still going to get 6 for x. So we could put in 1 for y, we could put in -2 for y, we could put anything in we wanted. We could put in 37 for y, and we would still get 6 for x. In other words, the y can be any value, but the x values are all going to be 6. So that gives us one point, which is 6, 1, a second point, which is 6, -2, and every point on this would have an x value of 6, no matter what the y value was. So let's plot our points. For our first one, we're going to the right 6 and up 1. For our second point, we're still going to the right 6, but then we're going down 2. And what we're going to end up with is a whole bunch of points that are along the same vertical line, because every x value will be 6. And in fact, the solution of our first equation would just be this vertical line. Now for our second equation in this system, let's start out here by using 0 for x. That gives us 1/6 times 0 minus y is equal to 1. Anything times 0 is 0, so that's 0 minus y is equal to 1. That gives us -y is equal to 1, and if we divide both sides by -1, we get y is equal to -1. The one thing you can do if you have fractional values like this in an equation, if you want to substitute a number in here for x, say, you could make it something that you know is going to cancel with the 1/6. For example, we could make x a multiple of 6, like 6. So let's try x equals 6 here. That gives us 1/6 times 6. And the 6's are going to cancel out, so we just have a 1. And if we subtract 1 from both sides, that's going to give us negative y is equal to 0. So we actually end up with y is equal to 0. All right, so now our 2 points are 0, -1. So for 0, -1, we're just going down 1 from the origin. And the point 6, 0, which we go to the right 6 and then stay on the x-axis. And that's actually, as we know, that's a point on our other line. So that is going to be our intersection point when we graph our second line here. So here's our second line. And as we already discovered, our intersection point is actually 6, 0. So that means our solution for our system is the point, or the ordered pair, 6, 0. Since we did find a solution, that means our system is consistent. And since we have two different lines, that means our equations are independent.